This program is brought to you by Emory University.
But when I've told students that we have somebody who's a Vatican astronomer, world-class scientist, they're interested. But when I say, and he was on the Colbert Report, now you've done something. Now you brought somebody we want to hear. Well, my name is Phil Thompson. I'm the director of the Aquinas Center of Theology here at Emory. It is my pleasure, along with some other folks here, to put Guy Consolmagno actually off the screen and live before you here tonight. Some other groups that are also sponsoring this event are the Center for Ethics, Paul Wolpe, Science and Society program here in Emory College, Ari Eisen, as well as the Candler School of Theology. So this is a collaborative effort. And fortunately, the way that I came about knowing Guy was going to be here, and he's giving a talk at Agnes Scott tomorrow night, which I recommend. Anybody who's not busy tomorrow night, you can talk about planetary ethics. But I found out he was coming to Agnes Scott, and I said, well, you know, I wonder if he's had some free time, and he might be able to come over to Emory. So he was very gracious. Agnes Scott was very gracious. He's actually spent part of the day talking with students at lunch, talking to them about the nature of knowledge. It was actually a fascinating discussion. We talked about everything from what is the nature of truth to what the Pope has for breakfast. So it was actually a very stimulating conversation. He was very gracious to do that. And he's been very gracious throughout the whole process. When I said, well, what can we do? You know, what would you allow us to do on Monday? He said, I'm yours on Monday. Do with me as you wish. And that's a very dangerous thing to say to a programmer like me, because we're going to make you do a number of events. But it's really been a thrill to be able to bring somebody at his level who's a major league scientist, as well as somebody who knows a little bit about religion and science, to Emory. He's got a couple of books. One, as you saw, The Heavens Proclaim, which is a lovely book. But the one my family and I read is called God's Mechanics, and it is an absolutely fun read. It's about how techies, that is, people in science and engineering, can think about religion, how he thinks about religion, how others like that can think about it. And it's the first book I can remember my wife and my son and I reading simultaneously in a long time. We can highly recommend that as a book. And by the way, the proceeds go to his order. The Jesuits, they do not go to him personally, so I'm not plugging this for Brother Guy personally, but it is quite a nice read. One other note for tonight, please, if you get a chance, take a look at it. We have a brochure talking a little bit more about the Aquinas Center. Thanks. And you can find out a little bit more about what we do. Our role here is to bring the Catholic scholarly presence to campus for the benefit of the Emory campus as well as the Atlantic community and Archdiocese as well. So we're thrilled to be able to bring people of this nature to the program. You've also got a flyer for the Atlantic Catholic Business Conference. If you're interested, that's coming up this coming weekend. On March 2nd, we have a Cardinal Walter Casper from the Vatican coming as well. So this is a very busy time of year for us. We've got some great programs coming, but we're thrilled that you're here tonight. And this is Galileo's birthday. So what an appropriate moment to invite Brother Consolmagno to come talk to us. And now, to introduce him formally, Ari Eisen is going to give you a little bit of his background. So thank you for being here tonight.
Thank you. Hi, folks. My name's Ari. I won't keep you long. I work over in biology in the ILA, Center for Ethics, and so I'm on both sides of the bridge a lot. And one of the things that really bothers me in 21st century America is that I have students come up to me and they say, "Oh, you mean you could be a scientist and believe in God also?" Very seriously. They say that very seriously. And it seems that we've entered a kind of strange period in American history, and it's a real pleasure to bring somebody who represents how science and religion have, as he puts it, coexisted without any problem, in people like Brother Guy for a long tradition for many centuries. So it's a pleasure to bring him here. He has a very rich experience. He spent time with some of my students today. It was a pleasure to see him do what he says is really his dream, is to be a professor, which he has done. He has taught before he became a Jesuit. He taught college in Pennsylvania. He's been in the Peace Corps. in Kenya. He got an undergraduate degree at MIT, PhD, University of Arizona. So he's done some amazing things, and I think we're in for a treat. So I'll turn it over to him, and as a kind of personification of how science and religion are in some ways one, and in other ways certainly complement each other. Brother Guy.
Thank you very much. In connection with the coursework that's been going on here, it was suggested the topic would be something about the nature of truth, and the nature of truth as it occurred in the time of Galileo and the time today. In order to do this, I'm going to be working a lot from material that was actually published in a book in 2000 called Brother Astronomer. So it's another plug, except the book's out of print, for whatever good that is. I do want to start with just a simple personal story, how I really got into the whole Galileo side of this. As a Jesuit, I have to do a certain amount of training, and part of my training was in philosophy. I did this at Loyola University in Chicago. And living in the Jesuit community there, the fellow who lived across the hall from me was a history professor, Robert Byerly. He was teaching a course at Loyola for history majors, seniors, and he wanted to teach them the difference between primary, secondary, tertiary sources. He's teaching them not just history, but how you do history. And he was going to use the Galileo affair as his case example. He invited me to sit in on the class, and for me it was great because I actually got to read Galileo. And I was able to relate to Galileo not as a historian, but as a fellow scientist, to read what he was saying and reflect about how his experience of coming to discoveries was very similar to an experience that astronomers even today come to. Now, primary sources are basically documents from the era. What Galileo himself wrote, what his contemporaries wrote, who were for him, who was against him. And the wonderful thing about Galileo as a course example was that many of these documents are available in modern translation in a book prepared by Maurice Funuchiaro from the University of California Press. And this is one that I would recommend if you want to get a start. Instead of trying to read what other people are saying about Galileo, read his stuff for yourself, make up your own mind. People who I know who have read this said, oh, I used to understand Galileo, but now that I've read the source material, I don't understand him at all. This is the success. The secondary sources are what has been written by scholars exploring the issues around Galileo. And for that, the literature is vast. It's also highly colored by the concerns, the predispositions, the interests of those writing the books. That's, of course, the nature of secondary sources. Then, of course, there are all the tertiary sources of the famous Galileo myth, like the famous play by Bertolt Brecht. You can't talk about Galileo without engaging these preconceptions, even though in virtually all cases, the myth has only the slightest passing resemblance to the truth. But as the saying goes, when the myth overtakes the truth, you print the myth. It's preconceptions. Preconceptions are both the bane and the heart of science. When a preconception turns out to be wrong, we mock it. We call it prejudice. When it turns out to be right, we call it insight. Now, the church has certainly suffered its share of attacks for stubbornly holding on to its preconceptions. Everybody knows how Galileo was persecuted by the church all his life for supporting the Copernican theory of the planets orbiting the sun. Everybody knows the old-fashioned theory of planets and the sun going around the earth due to Ptolemy was plainly wrong, and in the light of Galileo's proofs was rejected by all clear-thinking scientists in opposition to the church. And everybody knows that, nonetheless, the church couldn't bear to see the earth displaced as the center of the universe because it threatened the central role of the universe and humanity and God and the church itself. Of course, everybody also knows that what everybody knows ain't necessarily so. Just to take for an example, when the medievals adopted the Ptolemaic system as a way of illustrating the moral order, it was not to say that the earth was the center of the universe, but that the earth was the bottom of the universe. The last link in the chain of creation above the inferno that Dante so colorfully wrote about. A beautiful description of this, if you want to dig further, is actually C.S. Lewis's book, The Discarded Image. Most of us know C.S. Lewis is the author of Narnia. He had a day job. He was a professor of Renaissance and medieval literature, and he wrote The Discarded Image as a way of describing the medieval universe for people who want to read medieval literature so they would know the assumptions that those people were making as they described what they thought the universe was all about. Another example, the Copernican system, as Copernicus himself presented it, actually was only marginally more simple than the Ptolemaic system. His planets did not go around the sun in simple circles. They traveled around the average position of the sun, which itself did a little circle around this average position. They still had epicycles, they still had off-centered circles, just like Ptolemy used. The only difference was the sun wasn't moving, so that removed one term of the string of equations. But they had to have these bizarre epicycular motions in order to actually approximate the real positions of the real planets in the sky. Kepler's insight of ellipses as orbits was 80 years after Copernicus. Incidentally, after Copernicus published his book in 1542, it was highly esteemed for the next 50 years because of its improved predictions of planetary positions, which were used by the church to work out the reform of the calendar in 1582. But his tables were superseded by the improved observations of Tycho Brahe at the end of the century, around 1600. At that point, the Copernican work was considered by most astronomers to be obsolete. Now, who's Tycho Brahe? Tycho Brahe was the greatest pre-telescope observer of planetary positions. He actually had an 18-foot protractor that he sort of set up in an island north of Denmark that he would use to sight and measure the exact precise position of stars and planets, and use that to keep track of the motions of the planets through the stars. His data, the tables based on his data, were the data on which Kepler built his laws of planetary motions. And Tycho knew Copernicus's work. Tycho praised Copernicus's work. But Tycho decided on scientific grounds that ultimately the heliocentric system couldn't work. Given the state of the science in 1600, it's actually hard to fault his judgment. Kepler's laws were still 20 years into the future even then. Newton's laws of physics were more than 80 years down the road, and without both of those advances, the Copernican system physically didn't make sense. To take just one example, Tycho asked, why don't the positions of the stars appear to shift back and forth as the Earth goes around the sun? If you're here at one time and then 6 months later the Earth moves, one star closer to you will shift compared to other stars due to the motion of the Earth. It's called parallax motion. Tycho had actually measured the positions of stars at different seasons of the year to a few arc minutes of precision. 365 degrees in a circle. Each degree has 60 minutes. Each minute has 60 seconds. So an arc minute is a pretty tiny measurement. It's about 1 part in 10,000. And he did not see any shift in the positions of the stars from one half of the year to the other. Either the stars were incredibly far away, or the Earth didn't move. Now, it was generally believed by Copernicus and everybody else that the stars were objects embedded in an icy sphere surrounding the solar system, and that they shone by reflected sunlight, just like the planets and the moon does. Tycho calculated that if they were so distant as to show no motion, stars shining by reflected sunlight would have to be absurdly large to be as bright as they were. His observations were correct. His calculations were correct. Only his model for the origin of starlight was incorrect. And it would take 100 times better resolution, which was impossible without a telescope, to detect the apparent motion of the stars as the Earth moves from one side of the sun to the other. Those observations were only achieved in the 19th century. That was the state of astronomy when Galileo began to publish. These are the preconceptions against which his work was judged. Now, when we look at the nature of Galileo's persecution by the church, we see where the preconceptions and indeed the misconceptions are the most dangerous. Now, don't misunderstand me. This is not a talk about Galileo's trial. This is not a talk about why Galileo got into trouble. And this is definitely not a talk that's attempting to whitewash the church. What happened to Galileo was wrong. The church was to blame. It's important not to downplay the significance of the church's faults or its apologies. But if we don't see what the real crime was, we're more likely to defend ourselves against the wrong sin and let a terrible history repeat itself. So, what was the real crime? I'll just briefly mention. You want to know what really the church did that was so wrong? Look it up in a book. There's Amazon.com. There's a whole bunch of books. You could fill a library with all the books written about the Galileo affair, each one uncovering a different key to understanding what really went on, who the real bad guys were. If those don't work, try these. In fact, the whole story of why the church let itself be used to go after Galileo will probably never be fully understood, because it's impossible to recreate all of the circumstances that surround a whole affair. These books will tell you. It is possible, however, to draw some parallels between Galileo's time and our own. And that's what I want to do, and I want to do it not in terms of what happened in 1633 in the Galileo trial, but to move back to the 16 teens. In a funny way, modern astronomy has become so full of spacecraft and computer-aided images that we no longer instinctively identify those pretty pictures on the screen with actual lights in the nighttime sky. Our remove has paradoxically made us emotional innocents when we go outside at night and see the real thing. There's a story I heard from the director of the Griffith Planetarium in Los Angeles. About 20 years ago, there was an earthquake, the Northridge earthquake, in Los Angeles. The earthquake occurred about 6 in the morning. After the earthquake, for the next week, people kept calling up the planetarium saying, "Why did the earthquake make the sky look so frightening?" What do you mean the earthquake made the sky look frightening? And then they realized 1 million Angelinos had gone outside because of the earthquake. All the lights were out because of the earthquake. And for the first time in their lives, they had seen what the sky really looks like. And they were terrified. Something that actually, Isaac Asimov predicted in a science fiction story, Nightfall. When we escape light pollution, we can look up at a dark, clear sky with eyes no different from Galileo's, and we can be astonished just the same way he was. When I was a graduate student in the 1970s, I was studying the solar system at the Lunar and Planetary Lab at Arizona. I knew all about comets. I'd studied comets. I could quote facts and figures. I could write the equations that describe their orbits. I could write the equations that describe the growth of their comas and their tails. I could explain in painful detail the interactions of the plasma of the solar wind. I had that stuff cold. But my friend Bob Howell says to me, there's a comet you can see if you get up at 4 in the morning. And getting up at 4 in the morning, Comet West. I'd seen Comet Kohoutek. It wasn't all that impressive. So, why am I going to lose sleep over another comet? But nature called next morning at 4 a.m. So stumbling out of the bathroom, I thought, well, I'm awake anyway. Why don't I see what this comet looks like? It can't hurt. So I'm walking outside. I'm barefoot. It's cold. There's a stony driveway that I'm kind of walking around. As I look around the building, and there to the east was the most terrifying, astonishing, spectacular sight in the sky I have ever seen. It was as big and as bright as a photograph on a planetarium ceiling. This picture does not do justice to it, though it can give you an idea of how big it was compared to the horizon. It's not that the comet was impressive, it's that it was terrifying. In a world where the regularity of the stars is one of the few things that can be counted on and predicted, the presence of this flamboyant, looming stranger shook me to my core. I now understood why humankind has always seen comets as portents of evil. This is 1976, March 1976. Most of America missed Comet West. It came without a whole lot of warning or fanfare. It was really visible only for about a week, and that week it was mostly cloudy back east. And, of course, you could only see it at 4 in the morning. I had had this soul-shaking experience, and no words could describe it to my friends back east, what they had missed. From 1976, it was another 20 years before you could even begin to repeat that experience. Comets Hyakutake and Hale-Bopp in the late 1990s. So for 20 years, there was a whole generation of amateur astronomers who never knew what a good naked-eye comet really looked like. And those were more than 10 years ago. I dare say most of the undergraduates in this room have never seen a comet in the sky. And it may be another 10 or 20 years before they can. Of course, given light pollution, I suspect most of the undergraduates in this room have never seen the Milky Way, which is a real tragedy. Now, imagine the excitement among the leading thinkers of the Renaissance when a series of 3 bright naked-eye comets arrived in 1618. At that point, it had been nearly 40 years since there had been a naked-eye comet visible in the European skies. In 1619, the next year, the Jesuit priest Orazio Grassi of the Collegio Romano, the Roman College, described them in a 10-page pamphlet, an astronomical disputation on the 3 comets of the year 1618. The telescope had only been around for about 8 years at that point. So he begins by noting the recent advances in astronomy that the telescope had given us. Unlike earlier generations, we are no longer bleary-eyed from continually watching the stars for portents. Since we know that they are very far removed from us, we've been able to distinguish the circular motions of Venus and Mercury, and who is not embarrassed to note that what we see, the sun, occasionally disfigured by spots. We have laid bare the stratagems of Mars in approaching the Earth, and we have exposed the attendants of Jupiter and Saturn, hitherto uselessly hidden away. Until now, only comets have remained aloof from these lynx eyes. And then he discusses how the first 2 comets are very hard to observe. One was in Ursa Major in August, when it's close to the horizon. The second was whitish, loose texture of no considerable brightness. But finally, he says, on the 29th of November, the sky carried a very bright comet upward from the east, of such a brightness that all eyes and minds were immediately turned to it, and great throngs gathered in mountains and other very high places. And with his observations of the comet, Grassi proposed to consider those things that are within the bounds of our knowledge. For I do not approach you today as the sinister crow or the evil screech owl, the precursor of evils from these comets, forewarning of pestilences, famines, and the wars that they assist. If I merely explain the position, motion, and magnitude of these comets, I shall be satisfied that I have fulfilled my purpose. All Grassi wanted to do was to get a better idea of what a comet was. Now, Aristotle had maintained that comets were caused by gases rising from the Earth that glowed by friction when they rubbed against the crystalline sphere that held the moon going around the Earth. On the other hand, Tycho Brahe and Michael Metzlin, observing the comet of 1577, had found by parallax that the comet was more distant than the moon, and thus, by inference, comets must be objects out in the planets. And remember, how this parallax thing works, just as it worked for a body going around the sun if you just go from one side of the Earth to the other. Something close by will appear to move a lot when you move from one side to the other. The farther away it is, the more it appears to move compared to the distant stars. But remember, from 1577, when Brahe and Maechtlin had done this observation, until 1618, there had been no further naked-eye comet visible in Europe. There was no way for others to see for themselves what a comet looked like. All they had were written reports and artists' conceptions. The kinds of evidence that it's very easy for a skeptic to discount, especially if the evidence flies in the face of your well-established worldview. Now, the issue of comets was especially important to the 17th century astronomers for a number of reasons. For one thing, if comets really were planetary bodies, their orbits were very odd. Planets travel through the zodiac, places like, let me go back and do that again so you get an idea. They travel through Mars, Cancer, the planets of the zodiac. And they go backwards every now and then. These are, of course, observations if you are watching Mars night after night after night for many, many months. You would see Mars doing this little dance. But comets were not in the plane of the zodiac. They appear to move in straight lines. Their motion varies radically from night to night, speeding up and slowing down. Tycho himself suggested they had oval-shaped orbits, in total contradiction to the physics that said that all motion in the perfect world beyond the translunary sphere was circular motion because circles were perfect. Did comets actually cross the orbits of other planets? Did comets somehow travel through those crystalline spheres that held each of the planets? More intriguing to Tycho, he was not able to see any kind of retrograde motion. The retrograde motion was the excuse, that little backwards dance, that was the excuse that Copernicus used for having the Earth move around the sun. And that was, of course, why you needed the epicycler motion in the Tycho Brahe, in the Ptolemaic system. If Copernicus is right, then every body orbiting the sun outside of the Earth's orbit should, at some time or another, show retrograde motion. Comets didn't show retrograde motion, therefore the Copernican theory couldn't be right. Unless, of course, it turns out that comets aren't orbiting bodies at all, but just some kind of local phenomenon like a rising ball of luminous gas rubbing against the upper sphere where the moon is. It didn't occur to them the other possibility that the part of the orbit where they're going to be in retrograde motion is so far from the Earth that you can't see the comet. Anyway, in the comet of 1618, Grassi carefully measured the comet's position. He compared his measurements in Rome to those of his colleagues further north in Austria, and the result was they could not see any visible parallax. Indeed, both groups saw the comet occult a sixth magnitude star in Bootes on the same night, at the same time. You can see some parallax even with the moon, so you knew the comet had to be out away from the moon, farther than the moon. It's not in the Earth's atmosphere. It doesn't show retrograde motion. Therefore, Copernicus must be wrong. Bad news for Copernicus. That was his first and main point. In addition, Grassi noted that a comet's orbit was consistent with following a great circle in the celestial sphere, as you might expect for a body in a circular orbit around the Earth. Certainly not the kind of irregular motion you'd expect for a fiery cloud of gas rising from the Earth. And, given its distance, it's hard to imagine any kind of fire that could burn as bright as a comet for as long as a comet. Furthermore, he noticed that a line between the comet's head and the tip of its tail always pointed away from the sun. Grassi concluded that the comet shone by reflecting the sun's light, which we agree. The curve of the tail wasn't a puzzle, since as he understood it, the laws of perspective used by artists said such a curvature is what you'd expect by looking at a straight tail in an odd angle, which he got wrong, but in his defense, it should be noted that perspective was still a very young science in that time. But Grossi's third point was perhaps the most revolutionary. He looked at the comet through a telescope. He was the first person to do that. Now, if perspective was a young science, the telescope was in its infancy. It was only 8 years earlier that Galileo had written The Messenger of the Stars, when Galileo, with his telescope for the first time, had seen the disks of Venus and Mercury, the changes in the apparent size of Mars as it came close to the Earth, the sunspots, the moons of Jupiter, the rings of Saturn, all of those things that Grossi had listed in his introduction. In addition, for the first time, the Milky Way was revealed to Galileo as a collection of individual small stars. Galileo, the champion of the telescope, was the leading light of an informal club of scholars who called themselves the Academy of the Lynxes, taking for themselves the traditional cleverness and sharp eyes of the lynx. That's where that allusion came from, where Grossi mentions that only comets have been aloof from lynx eyes. Galileo had not observed the comets, because, of course, until then, there were no comets available for him to observe. Now, the telescope itself was controversial. Yes, for the first time, all the wonders of the sky could be seen, but also, for the first time, a scientist had to rely on some kind of mechanical device in order to study nature. And this was very unsettling, especially to those who didn't understand how the telescope worked. Plenty of people in Galileo's time were skeptical about the reality of the moons around Jupiter, especially since the best physics of the day, Aristotle's physics, insisted they shouldn't exist. Actually, I remember once a few years ago chatting with a very advanced amateur astronomer who was describing to me the first telescope he ever built when he was a teenager. He ground the mirror by himself. He bought a lens from a mail order shop. He installed the mirror in a tube. He put the lens in. He took it out by himself the first night, pointed it at Jupiter, looked at Jupiter, and he was terribly disappointed because he saw little dots of light on either side of Jupiter. And he said, "Rats, there must be a crack in the lens someplace, and I'm seeing internal reflections." Which, of course, raises the question, how did Galileo know that he didn't have internal reflections, that those moons really were real and not artifacts of the telescope? For the first time, he was using an instrument that nobody had much experience with. Given this controversy over depending on an artificial tool to look at the sky, in his book, Grossi patiently explains how the telescope could be used to prove the distance of an object. He says, "When the comet was observed through a telescope, it suffered scarcely any enlargement. Nonetheless, it has been discovered by long experience and proved by optical reasons that all things observed with this instrument seem larger than they appear to the naked eye. But, according to the law, that the enlargement appears less and less the farther away they are from the eye, such that the fixed stars, the most remote of us, receive no perceptible magnification from the telescope. Therefore, since the comet appeared to be enlarged very little, it will have to be said that it is more remote from us than the moon, since when this is observed through the telescope it appears much larger, but not as enlarged, of course, as the distant stars, which don't appear to be enlarged at all. Now," he ends, "I know this argument is of little significance to some, but perhaps they've given little consideration to the principles of optics, which, it must be understood, play a very important part in what we are considering." Grossi screwed it up completely, for quite forgivable reasons. He totally bollocks this argument. Astronomy would be a whole lot easier if Grossi's explanation were true, because finding the absolute or even the relative distances from planets to stars has always been really, really hard to do. Very tricky. The fact of the matter is, the magnifying power of a telescope stays constant no matter how far away the object is. You can't tell how far an object is by how much it's magnified in the telescope. Grassi's argument is flat out wrong. Now, Grassi was correct in observing that the telescope cannot make stars look bigger. He leapt to the obvious but wrong conclusion that that was due to their distance, not due to their small size in terms of the angle that they subtend in the sky. The trouble is that because of the wave nature of light, which no one would understand for another 200 years, there is a limit to how tiny an angle that a telescope of a given size can resolve. A telescope of Grassi's day would do well to resolve an angle of 5 arc seconds, 1 degree, 30 minutes, each degree, 30 seconds. Unfortunately, even the closest star subtends less than 0.01 arc seconds. Virtually all stars are smaller than this resolution limit in any optical telescopes, even the biggest ones we've built today, with a couple of exceptions. And that's a couple of exceptions of stars, not a couple of exceptions of telescopes. Even in the best modern telescopes, stars are still points of light. The comet of a nucleus, although it's a whole lot closer to us than the nearest star, is also a whole lot smaller. At 1 astronomical unit away, the distance between the Earth and the Sun, a 5-kilometer comet nucleus would only be as big as a star that is 4 light years away. So it too was well below the resolution of Grassi's telescope. And it too would look like a point of light regardless of how big a telescope he used. Of course, the coma would look bigger, but that point of light in the center would still be a dot. Grassi probably saw the bigger coma. Grassi probably decided that was just because he was looking at making fainter things brighter. But he saw the same point, and he leapt to this wonderfully logical but utterly erroneous conclusion. Grassi's final comment in that phrase, "I know this argument is of little significance," was especially unfortunate, given the fact that he himself really didn't understand optics. But then few people did understand optics back then. What Grassi was thinking of were those people who didn't believe the telescope actually showed you what was really out there, those who had doubted Galileo's observation. Grassi, like most of the Jesuits at the Roman college then, thought of himself as a friend and a defender of Galileo. For one thing, the Jesuits were bitter intellectual rivals of the Dominicans, another religious order. It had been a Dominican in Florence who had first accused Galileo of heresy. That alone would be enough to get the Jesuits on his side. But in addition, the Jesuits had been honestly excited and delighted by his discoveries. When Galileo first came to Rome, after the publication of the Starry Message, Ambassador of the Stars, the Jesuits held a celebration in his honor at the Roman College. An elderly Father Christopher Clavius, the Jesuit who'd helped work out the reform of the calendar in Pope Gregory 30 years earlier, he had used Galileo's telescope. He had enthusiastically endorsed Galileo's telescope. Actually, earlier, Clavius had written a letter of recommendation for Galileo to get a job. So they were in good terms. But when Galileo saw Grassi's book, he thought that last bit about people who don't understand telescopes was aimed at him. And what's more, he had 3 really strong emotional reasons to not want to believe that comets were distant astronomical objects. For one thing, as mentioned before, a real distant comet out in space caused problems for the Copernican theory. It didn't have retrograde motion, and it never occurred to anybody that the aphelion was going to be so far away that you wouldn't be able to see the retrograde motion. By the time a comet becomes visible, it's moving faster than the Earth, and therefore it doesn't give retrograde motion. All of which you might actually have inferred from Kepler's laws, which had been published by then in 1609. but no one but Kepler really understood Kepler's laws. Galileo certainly didn't. Galileo believed in circular orbits to the end of his days. A second and deeper problem for Galileo was that Tycho Brahe had used parallax to find the comet's distance, and Galileo hated Brahe and all he stood for because Brahe's theory of the solar system was the most serious rival to Copernicanism at the time. Brahe believed that the Earth is fixed, the sun goes around the Earth, but all the other planets go around the sun. In truth, the two theories, the Copernican theory and the Brahe theory, are really the same theory with just a different point defined as the central point in terms of observing. And so no observation of planetary motions, no observations of planetary shapes, no observations of crescents on Venus can distinguish between Tycho Brahe's theory and Copernicus's theory. And what's worse, Brahe's theory got around all of the scientific problems that Copernicanism by itself couldn't get around. And Brahe's theory was consistent with the best physics of the day. If you look actually at what people were writing about astronomy, not Galileo, not Kepler, but everybody else in the astronomical world in the 17th century, the heliocentric theory was not widely adopted until Newton and his laws came along 60 years later, in the 1680s. Because only then could Newton's physics finally reproduce Kepler's elliptical orbits, not the strict Copernican theory, from first principles. Which, of course, raises an interesting question to ponder. Given that state of affairs, why did Galileo believe in the Copernican view so strongly? In fact, you can look in Galileo's writings, and he was a strong Copernican even in the 1590s, well before he invented the telescope. Why? Where did that insight come from? Was it a prejudice or was it brilliance? If he'd been wrong, we know what we'd call it. Finally, I suspect there was a third reason why Galileo hated the idea of comets orbiting in space. After all, Galileo was the first person to see planets through a telescope, and stars through a telescope, and nebulae through a telescope. He was extremely jealous of his priority in this regard, but he never observed the comet. In the fall of 1618, he later wrote, he was sick in bed. His string of firsts had been usurped. He wouldn't be the last astronomer to think he owned a piece of a certain field, and certainly missing out on comets would have irritated him no end. The only salve to his pride would be to show that comets were not astronomical objects after all, but just reflections of light in the upper atmosphere of the Earth. To this end, a thin book appears in 1619, A Discourse on the Comets. The author is listed as Mario Guiducci, who was a friend and student of Galileo's. It starts out by discussing and dismissing the opinions of Aristotle and other classical scholars on the origins of comets, and it's full of fulsome praise of Galileo, including a gratuitous slam at another Jesuit, Christoph Scheiner, who had dared to publish observations of sunspots at the same time as Galileo. They fought over who was the first to discover sunspots. The answer was Thomas Harriot in England, neither of these guys, but that's so it goes. At that point, Guiducci begins his argument as to why the comet cannot be a body like a planet. First, he notes that a planet like Mars gets noticeably brighter as it approaches the Earth, but a comet is very large when it first appears and afterwards grows little or not at all for a very short time, subsequently diminishing during its remaining period until it's completely lost. One suspects that this is the work of someone who had not actually seen a comet. Only in pre-telescope days was it true that comets were large before they were first noticed. Secondly, he notes, correctly, on the rarity of comets. If the comet of 1618 had appeared before, the earliest possible apparition would have been the most recent bright comet, assuming, wrong, that all comets have apparitions that are equally bright. And that, of course, is 1577. But this, he argued, would require an absurdly huge orbit, which in fact we now know is the case for comets, and not absurd after all. Furthermore, it would be completely inconsistent with a body in circular orbit moving at a circular rate, since the comet was visible for such a short time, yet traversed such a large arc of the sky. Which, of course, he's right. It would be inconsistent with that kind of orbit. But he assumes that kind of orbit must be the kind of orbit that things in space have. Therefore, this couldn't be a thing in space. Of course, Kepler had already explained this with the elliptical orbits in 1609. Kepler had even sent a copy of his book to Galileo. Galileo never read the book. Actually, it's kind of understandable. Kepler wrote in this really turgid Latin that was very, very hard for anybody to understand. And Galileo was a university dropout. He basically flunked Latin, which is, he could do the math, but he couldn't handle the Latin. So he got a job teaching math and never got his university degree. So Galileo would have had an especially hard time figuring out Kepler's laws. Okay, Guidici then goes on to explain at some length to dispute the Aristotelian view that comets are ignited by the friction of gases against the celestial sphere, arguing wrong, that friction alone doesn't cause heat, and wrong, that fluids inside a sphere don't sense and are not moved by the rotation of the sphere. Still, up to this point, nothing had been said disputing Grassi's observations. In the second half of the book, Grassi's observations and theories are directly attacked. First, he proposes that comets, Guiducci says that comets may simply be reflections of light in our atmosphere, not real objects. That would nullify the parallax argument for reasons that isn't particularly clear unless there's equal reflections in both parts of the atmosphere. As an example, he points out that a rainbow will appear to move depending on the point of view of the observer. Why not likewise a comet appear to move where the observer is? Again, you get the idea that whoever's saying this has never actually seen a comet, and in fact, the refraction argument isn't logically worked out because comets show no preferred position relative to the position of the sun, unlike rainbows. He then goes on to discuss Grassi's other two arguments in favor of the comet's distance, and as we've seen, both of those were wrong too. And this discourse doesn't hesitate to point out the mistakes. First, he attacks Grassi's mistaken argument concerning how the telescope's magnification varies with the distance of the object. I had not intended to say anything about this argument, since it appeared to me to be quite incorrect and false, and I did not believe it gained assent except from persons of so little authority that it wouldn't be worthwhile to consider it. But mathematicians at the Collegio Romano have so high a regard for these arguments as to not only approve them, but to criticize those who had deprecated them, calling them little skilled in the principles of perspective and the telescopic effects, which they themselves had understood and observed by virtue of long experience and from theorems to optics. This made me reconsider. Long before the appearance of the work mentioned, Galileo had contradicted that reasoning and deemed it worthless, more positively and more publicly than anywhere else. Obviously, the author of the discourse saw Galileo as the victim and wanted his revenge. And then what follows is a detailed, if somewhat confusing, description of a telescope's operation. From his description of the changing of the telescope focus and how he saw halos around bright objects, you get the impression that the author has either a very flawed telescope or perhaps seriously bad eyesight, both of which were true for Galileo. Galileo had looked at the sun directly through a telescope. His eyes were not really that good after that. But the general thrust of the argument that Grassi's reasoning is flawed actually is completely correct. He's right. Discussing the supposed great circle of the motion, the author showed that every comet would have to have its own celestial sphere, and the absurdity of him of so many different orbits is self-evident. Clearly, he pointed out, circular orbits are impossible. Behind these self-evident absurdities, he saw the absurdity of Tycho Brahe's system itself, commenting that Grassi had accepted the same hypothesis as Tycho. Beyond the little which he has written in support of Tycho's opinion, I am left to affirm this by seeing how much he concurs with Tycho's other fantasies for the remainder of the book. If the comet's orbit is as these authors depict it, it is a great source of wonder to me that the fathers at the Collegio Romano have later been persuaded to call the comet the offspring of heaven. If so, it must be a triple goddess. It would have to be made of an inhabitant of the heavens, of the elemental regions, which is the part between the lunary sphere and the earth where the elements lived, the elementals lived, and also of hell, because it would go going right through the earth itself. It must, after running through the sky a long way, traverse the elements and then plunge into the infernal bowels of the earth. The sarcasm, if nothing else, is evident. The argument actually is wrong, but boy, the sarcasm is cool. Father Grassi, the guy who's the recipient of all of this, by most accounts, contemporary accounts, was a mild-mannered man. He was sensitive. He was a bit insecure. Documents in the Jesuit archives describe him as having a rather melancholy temperament. He suffered ill health most of his life. His response to this criticism was anything but mild. Perhaps part of his frustration with Galileo came from the restrictions against Copernicanism. The Copernican theory was appealing to many Jesuits because it was one of the evidences of the superior science to the West that the Jesuits brought to the court of the Chinese emperor. Kepler, who was actually on very good terms with the Jesuits, who could read Latin, but the Jesuits had just come through a bitter debate on a point of theology with the Dominicans. Their greatest and most respected theologian, Cardinal Bellarmine, had just died. In short, at that moment, they were in no position to get involved in yet another protracted controversy. And the same year that this book came out, 1619, as a response to the agitation stirred up by Galileo's earlier books, censors in Rome had ordered that every copy of the Copernican book must be corrected, to cross out the bit where it says the earth goes around the sun, and you write in, you can calculate by pretending that the earth goes around the sun. Where before, you could compare the different cosmologies with an open mind, the impolitic agitation of Galileo had brought about exactly what they feared, political interference with their science. Actually, as Owen Gingrich has pointed out, very few books of Copernicus actually were corrected the way that the censors commanded. This is our copy of the Copernican book at the Vatican Observatory, given to us from the Vatican Library, being inspected by a scholar of ancient books. It's not corrected. You can almost hear a plaintive cry as Grassi defends his reliance on Tycho Brahe. Is following Tycho such a crime? Whom instead should we follow? Ptolemy, whose followers' throats are threatened by the outthrust sword of Mars, now made closer, which is to say, the visible increase in the size of Mars in a telescope over the course of a year rules out the Ptolemaic system. Copernicus, but he who is pious will rather call everyone away from him and will spurn and reject his recently condemned hypothesis. Therefore, Tycho remains as the only one whom we may approve of as our leader among the unknown courses of the stars. This passage comes from The Astronomical Balance, which is a book supposedly written by Grassi's student, Orazio Salsi Solognesi, writing under the anagram of Lothario Sarsi Cingenciano. In fact, Sarsi attempts to put the arguments of Galileo in the balance to see which side's reasons are the better. In this book, he addresses Galileo directly, ignoring the fiction that Guiducci had been the author of the previous book. The book is as long as the previous two books put together. Sarsi disputes, point by point, every subject raised by Galileo, regardless of how irrelevant it is to the topic. Galileo says you can't ignore comets by friction. Sarsi proves counterexamples of how friction heats things. Some of them are drawn from legends and are clearly ridiculous, as the idea that you can boil an egg by spinning it around on a string. Others examples actually come from real experience, and his understanding of friction actually is better than Galileo's. Never mind that the point is pointless, since Sarsi and Grassi never argued that comets glow because of friction. He just wants to oppose everything that Galileo is for. Do smooth spheres cause the air inside of them to move when they spin? The answer is only important if you believe that crystalline spheres of the planets rub against gases to cause comets. And neither side is arguing that. But Sarsi still argues the point at great length. Actually, he's closer to the truth than Galileo, but it's so pointless. More to the point, Sarsi makes several strong and obvious arguments against the idea of the comet being a refraction of sunlight through a rising cloud of vapor. Galileo himself had said the parallax is such an object to be that of the sun, but Tycho Brahe's comet in 1577 had a measurable parallax, clearly located farther from the moon but less than the sun. On the matter of how a telescope works, Sarsi points out correctly that the telescope does two things. It makes small objects bigger, but it also makes faint objects brighter. This is 1619. By this point, Kepler's third book has come out, which explains how the telescope works in a long appendix. Galileo never got a copy of this book because Galileo had never written to Kepler thanking him for the earlier copies of the books. Of course, this is in answer to an argument raised in the disputation but off the point. Grassi was still wrong to think that the lack of magnification proved the distance of the comet. The second book made Galileo even angrier. In his copy of The Astronomical Balance, there are notes in his handwriting calling Grassi and his arguments oxen, lousy buffalo, elephantine. He worked for 3 years to write his response. In 1622, he publishes his text on the philosophy of science called The Assayer. The title is a pun in Italian. It contrasts a fine jeweler's scales with Grassi's rough astronomical balance. The Assayer is dedicated to his friend and fellow member of the Academy of the Lynxes, Matteo Barberini, who had just been elected pope, conveniently enough. He's got a friend as a pope. He's got other close colleagues who have now been appointed to high places in the bureaucracy. Galileo knew his time had come. The book opens with an imprimatur, the official pronouncement of the church that the book is free of doctrinal error. But in this case, the church censor, Niccolo Riccardi, who is a Dominican, not a Jesuit, goes even further and writes, "Besides, having found here nothing offensive to morality, nor anything that departs from the supernatural truth of our faith, I have remarked in it so many fine considerations pertaining to natural philosophy that I believe our age is to be glorified by future ages, not only as the heir of works of past philosophers, but as the discoverer of many secrets of nature which they were unable to be revealed. Thanks to the deep and sound reflections of this author, Galileo, in whose time I count myself fortunate to have been born, when the gold of truth is no longer weighed in bulk in some astronomical scale, but is assayed with so delicate a balance." Following that are several more pages of embarrassingly rich phrase, similar to the kind of critics acclaims you find nowadays in the front of a Tom Clancy novel. Among them is a 24-stanza poem that includes these lines, "Glory must be yielded by those daring modern explorers celebrated to the sky, who have charted unknown shores and newfound seas. You, however, add not just new lands here, but in the sky sublime you make appear new stars like these." That's my translation, but yeah, the poem is just as bad in the original. As had become his custom, Galileo wrote the book in Italian for the popular audience, not in Latin for the scholars. Galileo made his living selling books. Now, historians of science have often described how this book influenced the philosophy of science for the next several hundred years. Galileo demanded clear logic and experimental data rather than resting on the authority of ancient authors with their spinning eggs. Of course, you might suspect that Galileo disdained the ancient authors because he couldn't read them. Likewise, the acerbic tone made it a very entertaining bestseller. It was fun to read, as long as you weren't on the receiving end of the acid. The issue of the comet is supposedly the impetus for the book. Galileo pontificates on it, even though he admits he never saw it. But ultimately, it only plays a minor role. Indeed, the entire introduction is dedicated to attacking every person, both the scoundrel and the honest scientist, who had dared publish in Galileo's turf. He even mocks Grassi for hiding behind the name of a student. By contrast, he insists that the earlier book, The Discourse, really was the work of his own student, Guiducci. We actually have the original manuscript of the Guiducci book. Most of it is in Galileo's handwriting. And when you read it carefully, the Essayer contains enough scientific errors to embarrass even the most ardent Galileo supporter. To me, however, the most striking aspect is the contrast in tone between the Essayer and Galileo's first astronomical work, The Messenger of the Stars. The Messenger is a book that's filled with light. It's filled with the joy and the wonder of discovery. It's the work of a brilliant mind who could understand the things he was seeing for the first time through his telescope and understand their implications. 12 years later, in the Essayer, Galileo had become a querulous old man, more interested in scoring debaters' points than in finding out the truth for its own sake. And his triumph in the Essayer was a Pyrrhic victory. With his sarcasm, with his playing to the galleries, with his out-and-out lies, he managed to permanently alienate the Jesuits, the very people who might have been best positioned to defend him. 10 years later, when he goes on trial for reasons that aren't clear at all today, many of Galileo's friends in high places had died. And at that time, the Jesuits who could have defended him stayed silent. So, what can we learn from all this? First of all, it's important to remember that all scientific work is incomplete. Science consists of human-made theories that are rarely understood completely by most scientists and never completely true. Furthermore, the knowledge of the truth in one field is contingent on how advanced is our understanding in other fields. Grassi's arguments about comets failed because his understanding of optics was much too primitive. That, in turn, depended on understanding the wave theory that wasn't around for several hundred years to come. That's why science books go out of date. As we learn more in one field, it puts a new light on another field. We recognize things we thought were true are a little more complicated than we might have thought. Nobody who wants to study comets today ever bothers to read Grassi or Galileo, except maybe to pick out the details of their observations. Because obviously, our understanding of comets today has progressed so far beyond what either of those guys had to say 400 years ago. For that matter, I would expect that a textbook on comets from the year 2410 will make all of our work look really, really obsolete. I hope so. Notice the contrast between science and other fields. Philosophers still read Plato. Literature majors still read Shakespeare. Science books, however, are tossed away after a couple of years. Incidentally, that's one reason why the Bible is not a science book, why it's a scandal to treat the Bible like a science book, because you're saying you're going to toss it away in a few years. And if scientific truth is at best always incomplete, it is also always expressed in a context of other ideas. The Copernican system was a fine calculating device, but it only made sense in the context of Newton's laws and indeed only as adapted by Kepler into orbits that were ellipses. The same context made Tycho Brahe's cosmology superfluous and, in fact, misleading. Brahe could calculate the positions of the planets just as well as Copernicus could, but his bigger picture of what was going on was a cosmological dead end. Because we have to remember, after all of this, after all the horrible mistakes that Galileo made, all the nasty innuendos in Galileo's Essayer, at the end of the day, basically, ultimately, he was right. He was right. He's not completely right. Nobody ever is. But he was right in the sense that his direction was the direction to go in. His direction to get it was the way you find a deeper and more true understanding of how the universe works. Finally, though, it's worth stepping back and recalling a final truth about scientific truths. Science is done by human beings for very human motivations, driven and shaped by human concerns. Just look at the emotional climate surrounding the phenomena that started it all, the comet itself. Both Galileo and Grassi reacted with deep passion to this comet and to the things that the other guy said about the comet. Both were guilty of seeing in the comet only what they wanted to see. Both were influenced more by who they liked than by what was true. And both of them behaved as if they personally had ownership of that part of the heavens. Fact of the matter is, science has always had problems studying comets. Astronomy is not an experimental science. You can't go and create new comets and see what they look like. The phenomena of comets is spectacular, short-lived, and rare. As a result, observations can sound unbelievable, while they are also unrepeatable. Skeptics can't go back a year later and reobserve the object for themselves. By that time, the comet's gone back to the far reaches of the solar system. And you may have to wait, 41 years in the case of Tycho's comet of 1577, before the next observable comet comes along. And even then, as you saw from those earlier pictures of comets that I showed, no two comets are alike. So you can never be sure that what you saw in one comet is necessarily going to be observed in the next comet. Still, it was the jealous, possessive attitude of Grassi and Galileo, all the more offensive for coming from supposedly calm and rational men of science, that caused the final breach. The ill feeling on both sides that ultimately led to Galileo's trial in 1633 also ultimately gave support to the 19th century myth in books like Andrew Dixon White's of a myth of a war between science and religion, which is so beloved by both anti-religious bigots and anti-science bigots. And that was probably as great a disaster as any of the famines and bloodshed that the ignorant, superstitious peasants thought was going to come with the comet of 1618. Incidentally, 1618 was the year the 30 Years' War started. Thank you very much. Sure.
Well, if you want to get up and it's time to leave, go relieve your babysitters. Now's a good time, but we are going to take some questions. If you just want to step out and use the restrooms, come back in, you're welcome to. I want this to be relaxed time. Listening to Brother Guy, we're going to ask you, if you have questions, to come up to the microphone here. And as you do that, it reminds me of when I learned about the Copernican system and the Ptolemaic system and the differences between the two. And I was in a class, and our teacher had the students being the sun and the planets and so forth, doing the rotation, and she kept one student out who was a troublemaker. His name was David. So David wads up a bunch of paper balls, and as the persons are going around the sun, the person representing the sun, he throws the paper balls through them and yells out, "Meteorites."
He should have yelled out, "Comet."
That's right. So he made a mistake all the way around. Anyway, if you'd like to ask a question about what you've just heard, or we certainly will extend it beyond that. If you'd like to ask what the Pope has for breakfast or whatever is on your mind, we'd be happy. Brother Guy would be happy to.
I have to confess, I have no idea what the Pope has for breakfast.
So surely this has raised some questions here. Please come to the
Come to the mic so we can
microphone.
hear you and record you.
The only thing
Run up to the mic,
Yeah, you just have to
because
go with
it's
the
being
microphone.
recorded, so if you don't yell into the mic, we won't be able to hear you.
The only thing I ask is that you try to keep your questions fairly short. That's all. Now, come on up.
Don't be afraid.
You want to tell your, you tell your dad, he can come up.
Thank you, Brother Guy, for being here. I was wondering, in the Stephen Colbert little video that you had earlier, he was talking about a conference that the Vatican had in November. What was discussed at that conference?
It was actually not a discussion of the implications of extraterrestrials, which the way it would sound.
Okay.
It was actually a scientific conference on astrobiology. The Pontifical Academy of Sciences, which is an academy of 120 scientists from around the world, every faith, including no faith, I mean Stephen Hawking is a member, sponsored this conference to bring in people from the different fields that make up astrobiology, a few representatives of each of the astronomers, the biologists, the people wondering how life came about on Earth, to just exchange ideas and information with each other. And it was a purely scientific conference, because astrobiology is now a topic that is mature enough that we can make progress even before we find life elsewhere. I expect we will find life elsewhere. My favorite place is probably the oceans of Europa, but I'd be surprised if we didn't. Okay. And it's interesting to know, how would you know that it was life when you found it? What are the things we should be looking for? How do you devise experiments in a robot to figure out, is there life or is there not life?
Okay.
Those are all very important scientific questions.
Okay. And then another question I had was about, you're the curator of meteorites.
Yeah.
If you could just speak a little bit about that and what you do and what kind of collection you guys have.
The Vatican collection of meteorites, like most things at the Vatican, happened by accident. A wealthy French nobleman in the 19th century collected the meteorites for his own pleasure, and then in the early 20th century said, you know, the Vatican ought to have a natural history museum to go along with its art museum, and I'll donate part of my collection. At that point, the cardinal in charge of such things said, why do we need more rocks from France? We got plenty of rocks here in Italy. And it graciously said no. So he held on to most of the meteorites until he died in the 1930s. His widow then donated the collection. By then, the observatory had moved out to Castel Gandolfo. We had room to store them. So it started out as a collector's collection, a little bit of everything. More than 1,000 samples, about 500 different meteorites represented. My job is, first of all, to do research with those meteorites. I'm trained in meteoritics. My background at MIT was actually in earth sciences, not astronomy. And I've studied, the different classifications of meteorites. My particular research is to examine the physical structure. I measure their density, their porosity. We've worked out ways to do that without dunking them in water, which would contaminate them. So we have new ways of doing those measurements. I'm doing thermal measurements, magnetic measurements, basically physical property measurements. In addition, because we have such a broad collection, other researchers at other universities who need a small sample for their research will sometimes write saying, do you have a piece of this? Could I borrow it? Could I use it for destructive or non-destructive purposes? And so I've got to keep track of it and know who I've lent them out to and sent them back. And anybody who's collected things, whether it's baseball cards or whatever, in the middle of the night they get up and move around. I swear. So just keeping track of them, doing an inventory every couple of years is part of the job, just to make sure that the pieces haven't moved.
Thank you very much.
Well, you just answered a part of my question about what you do on your daily work, but I'd like to know a little bit about the position. How long has it been around?
I'll tell you a little bit about
what's the philosophy
Vatican
of it, and then the second part of my question is there a Vatican physicist? Is there a Vatican chemist?
Right. I'm not the Vatican astronomer. There are a dozen of us. You saw the picture of Jose Funes. It's pronounced Funes, not Fuentes. We are a dozen Jesuit scientists with a couple of more support staff in our community. We cover the entire range of astronomy from cosmology, the Big Bang, the mathematics of string theory, all the way to meteors and meteorites, so from the grand to the ridiculously tiny. And we come from 4 continents. We have Americans, South Americans, our directors from South America, Europeans, an African, and there's an Indian who's likely to join us in the next 5 years. My job when I got there was do good science, and that was my only assignment. Basically, we were established in our modern form in 1891 to show the world that the church supports science, because the late 19th century was when the myth began that there was a war between science and religion. It's a 19th century idea. It does not go back to Galileo. There were astronomers in the Roman college before Galileo in competition with Galileo, the guys who helped reform the calendar. So there had always been astronomers working in Rome. But in the 1890s, because of the unification of Italy, the Vatican was reduced to just the area around Vatican City. The old astronomy and the old telescopes had been taken over by the Italian government, so the Pope reestablished a new Vatican observatory. The Vatican is actually a dinky outfit for something that's trying to run an organization of 1 billion people who don't want to be run. There's probably only about 500 to 1,000 people who work there. The budget is smaller than the budget of the Archdiocese of Atlanta. They don't have hospitals and schools to take care of. Our budget is about 0.5% of the Vatican's total budget. And they don't have money to support other outfits. So while there are Catholic universities with all of that other science going on, there's not a particular Vatican institute that also does it. And there's a Vatican Pontifical Academy of Sciences, scientists who advise the Vatican on topics well beyond what the astronomers do. But they're in an advisory role. They're not being paid by the Vatican to do their work. It's actually kind of handy that they chose astronomy, though it was a historical accident, because most of the other realms of science nowadays involve ways you can make money. If we had chemists, we'd have people competing against useful chemical products. If we had biologists, we'd have people competing against useful biological or medical products. But there's absolutely nothing useful about astronomy, so we don't have to worry about that.
Thank you.
So you mentioned some of Galileo's erroneous theories, for instance, the one about the comets. My understanding that a very important for him theory was the one about the tides, which he thought was the ultimate proof of the Copernican system. Of course, that theory was also erroneous. It was perhaps Newton.
Galileo thought that the spinning of the Earth explained why there was one high tide every day. There's actually 2. He lived in the Mediterranean, where they don't have very high tides. Poor Galileo. All of this is not to say that Galileo was stupid. He was brilliant. He got so many things right that the things he got wrong sort of stand out like sore thumbs. But he was also very human. I'll tell you another Galileo story he was in this big argument with Christoph Scheiner about sunspots. Scheiner says that sunspots are due to little planets traveling between the sun and the Earth. Galileo says that sunspots are due to things actually stuck on the surface of the sun. Galileo says, you can test this theory. The idea of a testable theory was hot stuff for Galileo. He says, look at sunspots at high latitudes and near the equator of the sun. If a sunspot crosses the narrow part at the top of the sun very quickly compared to how long it takes to cross the lower part of the sun, then they could be objects that are all moving at the same speed in front of the sun. But if it takes the same amount of time for a spot to go from one side to the other, whether it's at the top of the sun or at the equator, then they're probably stuck to the surface of the sun. A brilliant insight. And of course, Galileo is right. Spots are stuck to the sun. Galileo then goes on to say, I have carefully measured the time it takes for spots at all these different latitudes, and they all take exactly the same amount of time to cross. Therefore, I'm right. In fact, the sun is a big ball of gas, and the rate at which the upper latitudes rotate is slightly different from the rate at which the equator rotates. And if Galileo had measured as carefully as he claimed, he would have seen that. So he was brilliant, and he ignored the bits of data that didn't fit with his theory. And boy, every scientist has done that. I've done that. I can really relate to that. And sometimes that's the brilliance. You know, when Hubble plotted his points of how galaxies moved, you go back and look at his data today and you go, that really doesn't prove the universe was expanding. But he was so convinced that the universe expanded that he said, well, I'll just shade things. And it kind of works if you kind of half close your eyes. And you know what? He was right. And he gets away with it.
One last thing. You talked a little bit about Orazio Grassi, Father Orazio Grassi. Maybe it could be added that he must have been one of the least vindictive people in the world, because during the trial, he was one of the most restrained.
Yeah, that's true. Grassi also did one other marvelous thing for astronomy. Grassi designed the Church of St. Ignatius in Rome. Anybody ever been to Rome? Has been to the Church of St. Ignatius? It was designed to be like a typical classical Baroque church, you know, wild on the inside, a huge dome that incidentally would have cast a really bad shadow on the Dominican house across the street. He was talked out of building the dome. Basically, they ran out of money. So instead of a dome, if you walk into the church, you look up and it looks like a dome. But when you walk under it, the dome looks like it's falling over on you because it's a flat roof with a dome painted in perspective on the flat roof. Why is this important for astronomy? Because 300 years later, another Jesuit looked at that flat roof, looked at the 4 pillars that were supposed to support a weight of a dome that's not there, and he used them to place 4 telescopes on a roof that was above most of the skyline of Rome. And from there, Angelo Secchi was the first to discover the markings on Mars that he used the word canali for, but what he saw were actually there. He was the first to classify stars by their spectra. He observed 4,000 stars and sorted them into different classes. And he was the first to really explore the solar corona to a point where the current NASA instrument looking at the corona has a long name, which is an acronym that spells out Secchi. So all of that was because of the church that doesn't have a dome. Yeah.
I guess I'm trying to think of a good way to phrase this. What astronomical discovery have you come across that gave you the biggest, wow, that's so cool?
Certainly the wow, that was so cool feeling that I had the biggest was seeing Comet West, but that was not my discovery. In a bizarre way, I had been measuring the densities of different types of meteorites, and I'd been doing this for about 5 years. And then a fellow from France, Pierre Rochette, showed up with a new gizmo. Everybody knows how science works. A scientist sees a problem, invents an experiment to test a hypothesis. Science doesn't work that way. A scientist gets a new hammer, bangs things with it, and see what happens, and then you gather the data. So this guy from France had a gizmo that would measure magnetic properties of rocks, quickly, painlessly. And so he had measured all the same rocks that I had measured the densities of. And so what do? Well, you plot one against the other and see what happens. And I saw a beautiful pattern. All of the H meteorites were here, all of the L meteorites were there, all the ones in between were there. It made a beautiful curve. It was so good that I'm going, oh my, I don't believe it. Wow. And it's a little thing like that that was impressive to maybe 5 people in the world. But it gave me just a little dose of a thrill the first time it came up on my computer screen.
We're going to make this the last question.
Okay.
Hello, brother. I was just wondering, how's your study in science strengthen your belief in God?
That's a good way of phrasing it. Some people ask, do you believe in God because of science? I was asked this by a newspaper reporter once. And, I said, I don't believe in God because of my science. I believe in God for lots of other reasons. And then he wrote it up, fortunately passed it by me before he printed it. I don't believe in God because of my science, says Brother Constantly. No. But if you already have the belief in God, if you feel that you're familiar with God and the way God has acted in your life because of your prayer, because of the things that have happened, because of what you read of how God has acted in Scripture, how God has acted in the lives of other people, and you get a flavor after a while. Yep, that sounds like him. That's his sense of humor, all right. Right. So he's going to be Son of God and Son of Man. I was expecting that he was going to be a human son with a sort of a God's adopted son. No, the other way around. He always does that kind of thing. When I see that same sense of humor played out in the way things work in science, where they're exactly the opposite of what I expected, but as soon as I see it, I go, of course. That gives me the feeling that I'm looking at the same hand. When I feel the same sense of joy looking at a computer screen that I have in those moments of prayer when suddenly God just comes by and says, just saying hi. And it's that same sense of joy. Then I feel, yeah, maybe the best way is to describe it like this. When I was 8 years old, it was the summertime, and I was up at the cottage in Lake Huron, where we had a summer cottage, and it was raining. My mom would pull out a deck of cards, and we'd play rummy or some such dumb game. Now, your mom can beat an 8-year-old any day. That wasn't the point of the game. The point of the game was playing this game with me, was her way of saying she loved me in a way that she couldn't just come out and say she loved me, because as an 8-year-old I would have gone, oh, Mom! When God invites me to play with him in the universe, I feel the same sort of thing, that he sets up a puzzle. He's playing a game. I solve the puzzle. He goes, cool, now let's try this one. I'm like the dog chasing after a stick. Throw me another one. To me, it's that sense of experiencing God, the Creator, when I've got my fingers dirty messing around in his creation. And I suspect if there is a painter in this room, you know exactly what I'm talking about. If there's a dancer in this room, you know exactly what I'm talking about. If there's an athlete in this room, you know exactly what I'm talking about. Those moments when you're in the groove and it's working right. Those moments are magical. Those moments are religious. And that's why we do what we do. And it confirms your sense of the goodness of the universe. Thanks a whole lot for coming.
The preceding program is copyrighted by Emory University.